Welcome to the Absorption and Emission Spectra game show. Test your knowledge against AP Physics students. So, who can tell me about emission spectra?
It's the wavelengths an atom or compound emits when it's heated or passed through a current.
That's correct.
Question 1. Emission spectra of atoms.
Emission
Spectra is the visible change in emitted wavelengths from the level change of photons. Photon movement occurs when heated or when light passes through.
What would be the opposite of emission spectra?
absorption spectra. It's the wavelengths an atom absorbs when it's heated or passed through an electric current.
That's correct.
Question 2. Absorption spectra. Absorption spectra is the visible change in absorbed wavelengths from the level change of photons. Photon movement occurs when heated or when light passes through.
True or false? Every atom has unique spectra and a specific range of colors they emit when heated.
True.
That's correct.
Question 3. Unique spectra of atoms. As each element is unique, so is their spectra. The components that differ elements such as number of protons, neutrons, and electrons are the same components that cause different emission and absorption spectra.
Now for bonus points. Can anyone explain why each element has a unique spectra?
Because they're different elements.
Incorrect. We were looking for the response of the varying arrangement of electrons and number of protons contributes to an element's unique spectra. How does a Bohr model help demonstrate emission spectra?
It shows the energy level change of photons between rings when they are heated or pass through an electric current.
That's correct.
Bohr models show a hypothetical view of the inside of an atom. The arrangement of electrons in rings is what makes absorption and emission spectra possible. Electrons absorb or emit energy in the form of photons. As electrons move to a lower energy level, photons are emitted to balance the energy change by releasing light. As electrons move to a higher energy level, photons are absorbed to balance the energy change by absorbing light.
Are protons, neutrons, or photons absorbed between energy levels?
It absorbs photons.
That's correct.
Photons are carriers of electromagnetic force in the form of light. Photons are absorbed between energy levels in a Bohr model to balance the energy change from electron position movement. Photons are what make the absorption and emission spectra possible.
Now, let's take a look at absorption and emission spectra graphs. Can anyone tell me which one is which?
The graph above would be absorption and below would be emission.
That's correct. Tell me how you actually know that. No? Okay. So the emission spectra can be differentiated by the colors on the spectra, which show an atom releasing photons. Absorption spectra, on the other hand, show dark bands on the spectra where light is absorbed.
Okay, can anyone tell me which energy level has the lowest energy? Ooh, me when I wake up in the morning.
No, I meant from the options on the screen.
Ground state energy level.
That's correct.
The ground state energy level is the lowest energy level in which electrons are in their natural placement. The ground state are the rings an electron can utilize closest to the nucleus. It is the state that the electrons return to once they release energy.
Let's shift now to understand emission and absorption spectra in a lab.
Now we're going to do a color test, a color flame test. So we're going to dip our Q-tip in water and we're using strontium chloride. And we roll a Q-tip in strontium chloride, but before we use our Bunsen burner, always demonstrate proper lab safety procedures. And then we take our strontium chloride and water solution and we put it in the Bunsen burner flame.
Whoa.
And now we'll be demonstrating with a copper 2 chloride salt. So we take our Q-tip, dip it in water again, dip it in our copper 2 chloride, and then put it in the flame. Whoa.
Now that was just a conceptual application, but did you know this also applies to astronomy? The astronomy application for an absorption spectra is associated with identifying stars. Determining an elemental composition of a star is possible utilizing an absorption spectra, as the relative abundance of an element within a star is directly proportional to the width of lines on an absorption spectra. The thicker the line equals a more abundance of that particular element. The density of stars can also be determined. A star with a greater density will have a higher number of collisions in its photosphere between its particles, which in turn translates to a wider spectral line. Furthermore, based on the elemental makeup and temperature of different stars, they emit different proportions of energy in each color. For example, most of our sun's energy, it's concentrated towards yellow. The different energy concentrations towards color has to do with the internal temperature of that particular star.
So, how can absorption lines be used to understand the relative abundance of an element within a star?
Specific elements absorb different wavelengths of light, so you can identify the different elemental components of a star.
True. That's correct.
Okay, so how can the relative density of a star be found using absorption spectra?
Blue is greater than red.
Incorrect. All right, last question. Why do stars emit different colors of light?
The different energy concentrations toward color have to do with the internal temperature of each star.
That's correct. No reaction. Okay.
Now we'll be using a Cooper chloride solution.
People don't say Cooper. It's gonna be different for. Okay. That's correct. Emission spectra. Oh.